So the good and the bad news is you need to learn these and sort of know how they work. And we're going to spend some time in lab looking at models and trying to figure out how to specify them as a list from model and sort of where things go. And when I say that, even in the lab, it's just, okay, well, what components go in what matrix in list row? So you got to use the label where they go. So the good part, so that's the sort of bad news, I guess. The good news is that someone came along in 1980 after list row has sort of become more popular. This is the picture. There is Peter Bentley, who I wasn't his student in the sense of I wasn't in his lab. I was my advisor was Steve Reese, but he was on my dissertation committee, and I took a number of classes from him and stuff. And he's the person behind EQS, which is another of the SEM software packages. In big part because he developed, along with David Weeks in 1980 or so, what became known as the Bentley-Weeks model. They took, as I'm sure you're looking at now, this sort of frustration with these large number of list row matrices and try to figure out a way, is there a way we can simplify this process down? Because 13 matrices seems like a bit much. So let's sort of cut it down to something smaller and see if we can't make it make more sense. So the big breakthrough is they do not differentiate between observed and latent variables. So anytime when you have the separation out, here's observed exogenous, observed endogenous, latent exogenous, latent endogenous. They just collapsed those down and said, okay, where are the exogenous variables? Latent or observed, doesn't matter. Where are the endogenous variables? Latent or observed, doesn't matter which one they are. And they sort of combine those matrices together to make it a little bit more simple. It sounds like it'd be more complicated because they're combining things together, but it doesn't. What's nice about it is it doesn't matter now whether you're separating things out to latent or not or whatever. It also collapses down the matrices that are separating out the structure and the measurement components, because it, again, mathematically it doesn't matter anymore what they are. It's really only theoretically that they're separated out. So we now get down to this much smaller thing. So instead of 13, we now have 5. Sounds a lot better. Okay, the 5 matrices instead of 13. The beta matrix of regression coefficients of DVs predicting other DVs. All right, so the beta matrix actually is a holdover from list row. Right? It means the same thing. These are etas predicting etas. Endogenous variables predicting other endogenous variables. Etas. You have a gamma matrix, which is the matrix of regression coefficients relating the etas to the xis, but the difference here, though, or I should mention, is that in beta you can relate measured and latent exogenous variables to each other, and in gamma now you can relate the measured and latent endogenous variables. Endogenous variables from the exogenous variables. Doesn't matter if they're latent or measured. In the phi matrix, this is a matrix of covariances among any of the exogenous variables. Doesn't matter if they're latent or measured. All right, so now we're going to have latent variables and the errors and stuff all in the same vector, in the same matrix. You have an eta matrix, which is the vector of the DVs, and you have a xi matrix, which is the vector of the IVs. That's it. We can have one, instead of having to have, like here, a measurement model for Y, a measurement model for X, and then a separate structural model. All of it is specified in one model. The measurement and structural components are all here, one place. I'll show you how that works in a second. We know that eta are all the outcomes. These are measured outcomes and latent outcomes, and we can relate them to each other via the beta matrix, right? How etas predict other etas. And then we can also relate the etas to the independent or exogenous variables through these xis here through the gamma matrix, and that's all we need to be able to do the whole thing. It sort of simplifies everything down to just a few matrices and one regression, one structural equation. And it makes things a lot easier. It may not seem like it so far, but it does. And the other thing that they did too is to a certain degree, when you're actually specifying models in EQS, and one of the reasons why I liked it, I originally learned on EQS, so one of the first programs for structure equation modeling that I learned, they didn't refer, in the background, there was etas, betas, and all that stuff, but everything sort of just turned into V's and F's, which I loved, and E's and D's. So you had variables, factors, and you had errors, you had disturbances, right? V, F, E, and D. That's it. So you didn't have to worry about sort of etas and epsilons and xis and all this other stuff. So notice that here we have V1, V2, V3, V4. Those are the measured variables. Measured. You have F2, which is a measured variable. They're all considered etas. Eta 1, 2, 3, 4, 5, because they are all endogenous sort of dependent variables. And so they're all being predicted by something else. And I can connect those to other etas via this beta matrix here. Notice mostly it's all zeros because for the most part we're saying these things aren't related. They're only related in a couple of places. And we're going to add to that this relationship between the xis are independent variables. So what independent variables do we have? Well, we have one measured independent variable, V5. We have an independent factor, a xi, right? Independent factor. We have 4 independent or exogenous errors, and then we have an exogenous disturbance. Okay. Class are good? So it doesn't matter whether it is a measured exogenous variable, a latent exogenous variable, an error, or a disturbance. All those things have been collapsed into being one vector, all being connected to each other via the gamma matrix. So everything's been collapsed down quite a lot, quite a bit. The only thing that's not shown here, that's not part of this, is that there is an extra phi matrix in which we are able to correlate things with one another. But in that case, everything correlates. So because you can only correlate independent variables, we can take the xis, any of these xis, going to be a 1, 2, 3, 4, 5, 6, 7 by 7 matrix, and we can specify how these things relate to each other, and we can specify that we want to estimate their variances. So a couple things. What do you notice about the beta and the gamma matrices? What's in them? Zeros, ones, and asterisks, right? Zeros, ones, and asterisks. That's all you get in there. What do you think those mean? It's code. You say it's a riddle? So, okay, so what do zeros are fairly obvious. What does zero mean? Yeah, it means don't do that, right? Like I think this is 0 times whatever it is. I'm going to multiply this by 0. What's a 1 mean? We're going to include that one, but I'm literally going, instead of estimating some kind of, remember the betas and the gammas are things we're trying to estimate. These are coefficients. These are the regression coefficients relating etas and etas. These are the regression coefficients relating the xis and the etas. So they're all things we're trying to estimate. But we're not going to estimate everything. There are certain things that we're actually going to fix. And we're going to say, look, I'm not going to estimate this. I'm just going to multiply it by 1. I just want 1 times whatever this thing is. And I'll talk about that in a second. The asterisk in here, and this actually is true somewhat of Literal and other programs, is where you're specifying I want to estimate something. The asterisk is something that it's just open in this matrix to say that that's what the program, like EQS or Literal, Lavon, that's what it's going to estimate. All right, so this is some coefficient I'm trying to estimate. This is a coefficient that I'm just assuming is 1. And all the rest of them are all coefficients, I'm assuming, are 0, that don't exist. Same thing here. I'm going to estimate that, but I'm just going to say that's 1. I'm going to say that's 0. There are certain things that I'm going to assume and certain things I'm going to estimate. I'm going to talk more about this in the next lecture, but the terms for that are often used with these is fixed and free. So if a number is specified in here, like we say it's 0, I'm saying that's a fixed parameter, right? I'm actually just saying it's 0. I'm not trying to estimate it. I'm just saying it's 0. Same thing with 1. I'm not going to estimate it. I'm just going to say that I think I'm going to take 1 times whatever it is and not estimate anything. It's only the asterisk where I'm telling the program or the mathematics behind all this stuff that I want to estimate that thing. This thing is not something that I'm going to just state is a given number. I want to estimate that value as part of this process. Same thing here. I want to estimate these. These I don't want to estimate. All these 1s and 0s I'm not going to estimate. I just want to state that there's 0s and 1s. So when would I do that? When would I state things as 0s and 1s? Let's look at this matrix, because it's going to be a little bit weird to sort of translate this around. Let's look at these sets of matrices and look at how this would look sort of drawn out as a diagram. So here's a diagram that corresponds to these matrices. Let's figure out how this works. This may look somewhat familiar. This is in the Tabachek and Fidel book. This is in that structure equation modeling. Again, back to skiing. Again, they always like skiing and belly dancers as their main source of examples, it seems like. All right, so what are our measured variables? So let's think about this. Let's think about this in both sort of Bentley, Weeks, and Lisserl. We have 1, 2, 3, 4, 5 measured variables. All right, so where were those? 1, 2, 3, 4. Notice 5 is not there. 5 is missing. Now, why is 5 missing? Well, because 5, if you look at 5 is the only measured variable that isn't dependent, that isn't endogenous. This is the only exogenous one. So that's not going to be with all the other endogenous ones. It's going to be where? It's going to be here in V5, because that's where the x's are, the exogenous variables. That's where they go. Okay? What else do we have? So we know we're specifying 2 factors. All right? So we have 2 latent variables. All right? So where do they go? Well, F1 is our exogenous latent variable, right? It has an arrow going that way. I also try to make it easier in the sense that the 2 red ones are exogenous, everything else is endogenous. All right, so everything that's blue should show up in the eta matrix. Right? B1 through 4, and then F2. They're all endogenous. And they just repeat here. Okay? So everything that's red, or potentially not red, because the E's and the D are not red, but V5 and F1 are the obvious sort of variables that are exogenous. But any other thing where there's an arrow going away from it, E1, E2, E3, and E4 are also all exogenous. And the same with D1. So all of those, the reason why those all go into the Xi matrix is because they all have arrows going away from them. They're all independent variables. Now notice where the asterisks are in the model. I'm trying to make it explicit. Okay, so there are 1s and asterisks all over the place. So there's a 1 here, there's a 1 there. Like all the errors, have 1s, and this one should, and it doesn't. Check out, this one should also have a 1. So a 1 as well. And then the asterisks, there's an asterisk next to E1, next to E2, next to E3, next to E4, D1, and they're also, it's actually in D1. I think that's, and then each of the pathways have, except for this one, there's a 1 there as well. Okay, so let's talk about, when we talk about model specification and identification, we'll get more into why this factor has a 1. It's a fixed variance, where this one actually has a 1 here. We'll talk more about that later on. But let's just assume this is how it got specified. So where you see these 1s is where in the matrices their 1s are going to be in those matrices, right? All the asterisks is where you're going to see them. The problem is not all the asterisks show up here. There's 1, 2, 3, 4, 5. So all the structural asterisks show up here. Structural, right? So that means 1, 2, 3, 4, 5. Okay, so these are the structural sort of predictions. All these other ones, the asterisk next to E1, next to E2, next to E3, E4, D1, all of those are not found in these matrices. They're found in the phi matrix, which is where we can specify the variances and covariances of all the exogenous variables. Oh, I'm sorry. That's my fault for this. This should be labeled. This really should be D2. Because so in EQS, what they typically do is if this is F2, then the corresponding D is D2. It's technically the first D. I think that's why I labeled it D1. That makes sense? There's only one D. So I labeled it D1 here, but really it corresponds to the number that goes along with the factor. Because this is F2, this one is really D2. And that's what's in this matrix, is D2. But notice there's only one D in the whole thing. All right. No, that's a good catch. One of the things I said I'd do last time was to talk about how exactly, like, what does all this mean? Like, how does it work? When you have, this eta matrix that equals a beta times eta plus the gamma times xi. If you take each one of these things at a time, so if you look at V1, you can actually turn these into a series of just equations on their own. So let's do that and see if we can figure it out. So if we start with V1, so if we target just V1, everything that's in the beta, like this row and this row in the gamma matrix, all relates to V1. And so telling us what V1 then is predicted by. With me so far? So if we start with V1 here, start with V1, it's going to say that V1 equals to, well, not Y, V1 equals to what? So if you look at the first row, these are all zeros. So it's telling us that V1 is not predicted by any of the other etas. Right, so there's no etas at all in there. It's all zeros times everything. Remember, when we do matrices, you're going to take the row this way times the column. So it's 0 times V1. Obviously, we're not going to pick V1 with itself. So V1 times 0, 0 times V2, 0 times V3, 0 times V4, and then it's not being predicted by F2. Okay. But then we go over here. It's not being predicted by V5. You're getting an asterisk here, so it equals an asterisk times what? An asterisk times F1. All right. And then we're getting a 1 times the next one, which is E1. So we're going to add an E1 here, and it's just 1 times E1. And that's basically the equation for V1. V1 equals to an asterisk times F1 plus 1 times E1. Right? Let's go to the next one, V2. V2, getting a similar treatment where it's these like zeros all the way across, so there's no prediction by another eta. By the way, let's back up. Since Lauren wasn't here, what's What's the difference between an eta and a xi? What's the difference between an eta and a xi? Right, so xi is exogenous, eta is endogenous, which is why you can have etas predicting other etas, right? Because once they become endogenous, they can predict each other and they remain endogenous. But the exogenous variables, you can't predict those. They can only be predictors. They can only be independent variables, which is why they only appear here times the gamma matrix. So the beta matrix relates etas to other etas, and the gamma matrix relates xi's to etas. Right? So the exogenous to endogenous variables, that's all in this gamma matrix. All right, so if we're looking at V2, so V2 is not predicted by any of the other endogenous variables. So there's no cross anything here, right? So we're going to leave all that stuff out. But it is predicted by, if we go back across here, so it's not predicted by F5, which is the first thing, right? It is predicted by F1, just like this one is, star F1. But instead of being predicted by E1, which is the next one on the list, right? It's predicted by the next one, which is E2, which makes sense. It's V2. So 1 times E2 is what we're predicting for V2. Make sense? Maybe? Sort of? Okay, questions about that? Is that clear? So let's keep going. So we have V3. V3 now, all right, does have, sorry, if you look at V3, V3 equals, now there is something here. If you go across, there's a 1. Okay, so now V3 is getting predicted by the very last one, 1 times F2. So V3 is getting a 1 by F2 plus, that's it, at least for the beta matrix. And then when we go to V3 over here, it's also getting a, so it's not the first one, that's 0, 0, 0, 0, 0, and then 1. So it's getting a 1 times E3. Okay? About V4. Variable 4 is now getting 0, 0, 0, 0. Oh, there's an asterisk on the very last one, so it goes with F2. So it's getting an asterisk times F2 plus. And then if we're going across to V4, it's getting all the way down to the second to last one, which is E4, 1 times E4. And then last, we're getting there right in just a second. So I'll explain that in just 1 second. So then F2 is not being predicted by any of the other etas, right? So it's getting nothing by another of the exogenous variables, F2. But because it is endogenous, it is getting a bunch of stuff going on over here, right? So it's getting an asterisk times V5 plus, it's getting another asterisk times F1, and then nothing, 0, 0, 0, 0, then 1 times D, or really, yeah, D2. Okay. So this is basically, and we could have left the zeros in there, like multiplied the zeros and left them as part of the as part of the equation or whatever. But instead of trying to include all the zeros, there's basically zeros are saying just leave them out, don't estimate anything. So then if zeros mean leave it out, don't estimate it, what do ones mean? Put it in, but we're not estimating either. So zeros mean we're just saying 0 times that thing. All right? So if I put a 1 in there, it means I want 100% of it. Right? So I'm not estimating anything, I'm just saying I want all of D1. So this is going to be plus all of E1 plus all of E2. Right? So instead of trying to estimate something, I'm saying I want 100% of it. Because whenever you see an equation like even something simple like y equals b1 x1 plus E, it's sort of implied that there's a 1 here. We're not estimating some portion of it in that equation. We are estimating 100% of it. Make sense? So then, Lauren, what then are the asterisks? So it's not that it's a different percent. Yes, actually that's true, but these things we're not estimating these. We're just saying, like, I want 100% of D2, I want 100% of E4, and all the zeros mean I don't want to estimate anything. It's just I'm assuming they don't exist. So then, what do the asterisks mean? Yeah, these are the things I'm specifying in the model that I actually want to estimate. These are the slopes. These are the loadings, the coefficients, the things we actually want to estimate in the model, where everything else is fixed. So this is fixed at 1, fixed at 1, fixed at 1, fixed at 1. All the zeros are all fixed at 0. And then the term for it, whenever you see an asterisk, is that it's free. So it's free to be estimated, right? We set it free. That's the asterisk means that we're telling the program that this is free for the program to estimate. Anything that has a number near it is we're basically saying don't estimate that. We're fixing this as a specific value. You don't have to estimate those values. Okay. Now there are other parts of this where there are other asterisks that we need to take into account, because this just gives us the sort of relational, the structural and measurement estimates that we need to make. But the part that's left out is what variances and covariances need to be estimated. So that's in a separate matrix. That's in this matrix. So in the phi matrix is where we tell the program what things we want to estimate and what things we don't. So in this particular example, we're estimating almost all of the variances. So all the variances, and we can only really estimate variances for exogenous variables. So these are all the same variables that are in that Xi matrix. So all the Xis we're going to estimate a variance for. And we can only estimate covariances between Xis as well. So what this means is that we're specifying here that I want to estimate the variance of V5. I don't want to estimate the variance of F1. I'm actually going to fix it at 1, and I'll talk about that in a second. But I do want to estimate the variance of E1, the variance of E2, variance of E3, variance of E4, and the variance of D2. All those are going to get variance estimates. All the zeros on the sides over here are all telling us, or on the off diagonals, are telling us that we're not estimating any covariances among these. So there's no sort of unstructured relationships. Everything is just we're estimating variances, except for in one case where we're fixing the variance. So all the off diagonals are 0 to tell us that we're not correlating anything. So let's look back at this, the model, and see if I can get it to fit in with what I already drew. The matrix part of this, right? The matrix components that we just saw correspond exactly to everything that's in this diagram, except for the one mistake that someone pointed out, that this is not D2, right? This should be not D1, but D2, right? Then everything else sort of lines up. So notice where the asterisks are, notice where the 1s are, and then also notice things that are missing, right? So anything that's not in this model, like there's no arrow going from, say, this factor to this item, right? So we're assuming that's a 0. So any arrow that's not there is a 0 that was specified in that matrix that we were just looking at. So go back to what's going on with V1. Well, V1 is being predicted by, so if you look at V1 is predicted by what? So V1 is predicted by F1 here, right, with an asterisk. And it gets an E1 up there. It's times 1. There's an asterisk there to indicate that we're going to estimate the variance of that as well. If you look at V2 is down there at the bottom left. It's predicted by F1 and also E2. All right. V3. Now V3 is a special one. It's got 1 times F2. V4's got a asterisk times F2. They each have their errors. And then factor 2, the blue ski satisfactory circle there, is the only factor that's being predicted by something else. It's predicted by both F5 down here at the bottom, and that's being estimated. And then it's also being predicted by F1, and that's estimated. So where these things, a couple things that we'll get into in this very next lecture is like these factors don't exist, right? They're not real things. They don't exist, and we can't measure them directly. So we have to make them exist. We have to give them some kind of numeric scale. And there are 2 ways to do that. We can either give them a sort of artificial scale by giving them like a z-score metric and just saying, look, I want their variance to be fixed at 1, so it's like a z-score. Or I could attach the factor to one of the items, like snow satisfactory, by 1 to say, whatever this is, I want this ski satisfactory or ski trip satisfaction factor to match the scale of snow satisfaction by fixing that 1 to 1. So that's why this one, ski satisfaction, has a 1 going to V3. But because we fixed this 1 to 1, we can estimate both of those loadings with asterisks because we don't have to, we just said, look, give it an artificial scale. But this one actually has a real scale that is now tied to snow satisfaction. So everything on here tells us like what is being estimated, what's fixed, what's free to estimate, and all that stuff is all here, and it all matches between these two. So let's say I wanted to do something different. I wanted to add to this model or change the model somehow. So if I decided to go, say, from this sensation seeking, and I decided to then also predict factor 1 with it, that's going to change this these matrices. These. It's going to change these matrices, right? I'm now going to have a relationship between F2, right? F2 is now also going to, F1 is also going to be predicted by something which would move then F1 over to an eta, because it's now endogenous. It's no longer exogenous anymore. If I decided to instead say, look, all right, this model doesn't fit very well, so I'm going to try to see if there's something else I can do. And let's say I decide to correlate V5 and E4, these two variables. I try to throw a correlation in there to make the model fit a little better. That's going to have 0 impact on this because it's not part of the structure or measurement. But all of a sudden now, between V5 up here at the top and say E4 down here on the side, right, there's now going to be an asterisk because we're now going to tell in the phi matrix that we're now going to estimate a covariance that we weren't asking for before. So that's how these matrices all get sort of impacted or affected by your choices of where and what you're estimating. Okay.